Welcome to the class. Today we will start with molecularity. Basically, molecularity means the number of molecules involved in the reaction, the number of reactants. Now, molecularity can be of many types: unimolecular, bimolecular, trimolecular. Okay, so let us see the example for unimolecular, where only one compound is the reactant. Okay, only one compound is involved, that is ammonium nitrate. So here you can see to your left hand side only one compound is involved, so that is your unimolecular, one molecularity. Next, 2HI means HI plus HI, there are two molecules involved, so it is bimolecular. Next, total you count 2 NO plus 1 O2, so total 3 molecules are involved, 3 reactants are there, so it is trimolecular. Next, when we go beyond trimolecular, that is more than 3 molecules, it is very difficult for the molecules to collide with each other, because you see the probability is lessened now. Hence, beyond the 3 reactants, what happens? The complex reactions occur. Complex reaction means those reactions in which more than 3 steps are in, means more than 1 steps are involved. Okay, so that is happening for more than 3 molecules usually. Next is the how we can determine the molecularity of a complex reaction. You see, in every step you will get molecularity, but the slowest step, the step that is occurring very slow, the slowest step helps in determining the rate. So it is given here, slowest step is the rate determining step of the complex reactions. Next, let us talk about the integrated rate equations. You see, we have talked about instantaneous rate equations as well as average rate equations. When we say average, we mean to say comparison between two things, right? We will take out the sum of those two comparisons divided by the total number of comparisons that you have made. Clear? So that is your average, that is the mean. But when we talk about instantaneous, we mean to say we want to determine something, we want to take out a value of a particular thing only at a particular time, so that is the instantaneous rate equation or instantaneous rate. So now you see it is a constant in every term, and since we determine the instantaneous since it is very difficult for us to determine the rate law based on instantaneous rate equations, because every time it is changing, right, and it is constant, so you cannot take the average also. Now what to do? When something is constant and you have to take out at every step, now you cannot take out the average, that will give us the wrong answer. In that case, what to do? What we will do? We will just integrate it. Integration means bringing together, okay, bringing some values together. We are doing summing up by some other functions. We are not doing addition here, but integration means bringing together, just like we are doing sum, addition, but it is not purely addition. We have to just bring all the factors, all the values together. Now let us move on to the first zero order reactions. What will be the integrated rate equation for a zero order reaction, and how we can determine the rate constant? So let us consider a reaction where R is converted to P. So it's simple, R is reactant and P is product. Now how to express the rate equation? Rate is equal to K, then concentration of the reactant raised to the power order. Now we know that order is 0, so we can put here 0. Okay, so rate law is determined based on the concentration of the reactants raised to the power order. Clear? So anything raised to the power 0 is 1, right? So K into 1 is equal to K. Other things are same here. Now bring the dt that side, okay, near K. So you are left with differential of concentration of R equal to K dt. Okay. Now take the negative side to the right hand side, or you can say if we put a negative both sides. This is actually happening here. We cannot take the negative, that is -1, to your right hand side just like we want to. So what is done here? We will putting a -1 both sides, means multiplication of both the terms with -1. So here it will become plus, and here you are left with minus. Okay, so this is the thing basically, but in short we say that minus is taken to your right hand side. Okay, actually we cannot take like that. Now we have obtained this, the concentration of R equal to minus K dt. Okay, so this is the differential rate equation that we have got. Now we will integrate both sides. Okay, so we are going to use the calculus formula or integration formula, that is integration of the x is x. Okay, so this is a formula that you have to memorize, and I think so you have already learned in mathematics this. Now when we integrate, suppose this is x, what you will get? D of x is x, right? So in concentration of R is left. Next, you see what I have said, we integrate something that is changing. Okay, we are not talking about a variable, but at every point we are getting different values, right? So that is constant. Okay, not variable. And when we integrate, we tend to integrate something that is actually changing, so we cannot integrate a constant here that is fixed. Clear? So here you say that K is a constant, so K will be outside. We are not integrating the things that is constant, so constant will be outside the integration sign. And what is left here? Dt. So dt, you know, integration of dt will be t. Clear? And I is a integration constant. Next we will move on to another step here, different from what we have done here. So now we will consider the rate at 0, at time 0, when we haven't yet started the reaction. Okay, when time was 0 means the reaction has not occurred till now. That means time is equal to 0. When time is equal to 0, there was no reaction occurring, hence the concentration of the reactant will be the initial concentration, and let the initial concentration be R0. Is it clear? When, see, a reaction is occurring, right, and time is moving on, but when the reaction has not started, we will set the time as 0, and at this 0 time, since there is no reaction occurring, the number of reactants that we have taken will be as it is. So let us consider that the initial reactant taken is R0, and it will not change because you have not started the reaction yet. Clear? So the concentration of the reactant will be R0 and time is equal to 0. Now you see we can put it here, right? So the concentration of the reactant is R0 and time was 0, so it will be minus K into 0 and I. So this will become 0 and we will get the value of I as concentration of R0. Now this value you have to put in equation 1. Just put the value of I that we have got here. What you will get? Concentration of R equal to minus KT plus concentration of R0. Now bring KT in one side, and what you will get? R0 minus this KT. If you bring this side, it will become plus, right? So R0, concentration of R0 minus concentration of R divided by this T. Is it clear? So this is the final derivation that we have obtained, and as you can see in the graph, concentration and time versus. Okay, so this is a graph where concentration versus time is given, and you know that initial concentration was what? R0. Okay, and time was T. At 0 all the reactants was present, but as time is approaching, the concentration will decrease and the slope obtained is minus K. If we plot this, okay. Next example is decomposition of ammonia is an example of zero order reaction. Is it clear? And we have just written here that the rate is equal to K concentration of the reactant, that is ammonia, next to the power 0. Remember one thing, don't put here 2 by mistake because it is the order, it is not the coefficient. We have already discussed that this order sometimes becomes equal to the coefficient, but it is not always the same. Accidentally it sometimes become equal, but it's not same. So the power is not this 2 or 1 or 3. Okay, so rate is equal to the K rate constant. Next we will talk about the first order. For first order also we'll start in the similar way, and if you have learned the zero order, it is very easy for you to determine the first order because all the procedures are same here. So R is converted to P, reactant product, and R is given how the rate law is written, concentration of K into concentration of R to the power order, and order is first order, so we will put a 1 here. Okay, so we are left with Kr only. Next what we will do, again this minus will be observed here in your right hand side, and then you see differential of R by dt. Okay, and this is also concentration of R, so we will bring this R in place of dt and dt will go in place of K. You can see here. Okay, differential of R by concentration of R equal to K dt. Next we will integrate, and one formula is used here, that is 1 by x dx, or dx by x give us ln x. Okay, and then dx, concentration of dx is equal to x. So two formulas we are going to use here. This is already used in case of zero order, so this will be used now in first order. Okay, so you can see here, if a concentration of R is said to be as x, then how it is dx by x, right? So integration of dx by x is given as ln x. X means concentration of R. Okay, next again, since K is constant, this will come outside the function of integration, and you are left with integrating of dt. So you are left with t. We have already discussed this. Next is I, you have to put after integration. Again, using the same method, we will consider that the time is 0 and the concentration of the reactant is R naught. Okay, initial concentration of the R is not going to change at all because reaction has not started and we are at time 0. So ln, in place of this equation 1, you can write in place of concentration of R naught. Okay, t is 0 here, so I value you will get this ln R naught. Again, this in place of I you can put this value. So from 1 you will get ln R equal to minus kt plus ln R naught. So this was I that we have put the value. Next you bring the R naught this side. Okay, it is similar to log. Okay, the functions of ln natural logs are similar to the log, okay, whose base is 10, and this, for this you know its base is e here. Okay, small e. So this formula ln x minus ln y is equal to ln x by y, means log x minus log y is equal to log x by y. So similar formula. Okay, so this, if you bring this side, it will become ln concentration of R minus ln concentration of R naught. So ultimately you will get ln concentration of R divided by divided by concentration of R naught equal to minus kt. Now bring k in one side, you are left with 1 by t. If you bring the k this side, okay, suppose you bring the k this side, you are left with k 1 by t ln concentration of R naught by R. So now you observe one thing here, this R naught is in the denominator but now it's in the numerator, because you see, let me break it down, although I thought you will be able to do it. So it's like this, no, we have multiplied minus on both sides, so you will get kt. Now you see it's negative here, no, so it means what, it will become reverse. Okay, let me explain this. Now if I put a minus here, what it will become, it will become, this will become plus, no, so ln y minus ln x. Clear? So you will get ln y by x. Understood? So it is inverse now. Next, in order to convert the ln, in order to convert to log, the conversion factor is 2.303. You already know, okay, these things, so I am not going to go in details for this. So when ln is converted to log, you have to multiply one term, one conversion term, that is 2.303. Next, all the things are same. So you will get log of R naught by R is equal to kt by 2.303. You can leave it here or here, your wish. Okay, next we are going to get two graph here. This graph you already know, because time is increasing, the concentration of the reactants will always decrease. Initial concentration will always decrease. Next, the inverse. Okay, next the slope is increasing here, k by 2.303. when we take log of r naught by r, you see, if you make it very easy, this term is equal to this term. If this is increasing, then this will also increase now with time, so the slope is also increasing in the upward direction. Next example of first order is C2H4 plus H2 will give C2H6. okay, so this it will be H6.